Welcome to this explainer. Today we're doing something a little different. We're looking down, way down. We're going to completely demystify the incredible, complex engineering hidden right beneath the tires on your daily commute. Because from a field engineer's perspective, a highway is definitely not just rocks poured on dirt. It's actually a carefully engineered, living system with a pretty fascinating life cycle.
Think about this fraction for a second. 1/3. It might sound simple, but it actually represents countless saved lives. Today's traffic fatality rate, when we look at it in terms of driven distance, is just 1/3 of what it was back in the mid-1960s. That massive drop isn't some happy accident. It's the direct result of the continuous, rigorous problem solving from the field of highway engineering that we're about to explore together. Here's our roadmap for the explainer. We'll be hitting 1. Environmental planning, 2. Geometric design, 3. Pavement and rehabilitation, and 4. Roadside safety. Let's dive right in.
Section 1. Planning and environmental impact, before the shovels hit the dirt.
Long before any heavy machinery even shows up on site, engineers have to navigate a massive, complex maze of planning. And the absolute backbone of all this strict preparation is the National Environmental Policy Act of 1969, or NEPA for short. It's the key federal environmental statute for highway projects. Basically, under NEPA, incredibly detailed environmental documents have to be meticulously prepared before a single drop of concrete is poured or a surveyor even steps foot in the mud.
And honestly, the sheer amount of things planners and field surveyors have to juggle is just astonishing. We're talking about managing air quality impacts, dodging wetlands and streams, and protecting historic and sometimes even prehistoric sites. On top of that, they're ensuring endangered species are safe, mitigating traffic noise, and preserving farmlands. It turns out building a road is an exercise in extreme environmental balancing.
Section 2. Geometric design, the skeleton of the road. So how does the road actually take shape? Well, the highway skeleton is built through a rigid transportation development process. We move step by step from the planning and environmental phase we just talked about, straight into location and design. Then we acquire the right-of-way, and finally we hit construction. It's a very systematic flow designed to bring the blueprint to life.
It's during that location and design phase where geometric design totally takes over. And this is where the intense math happens. Engineers are calculating horizontal and vertical alignment, ensuring safe site distances, and computing cross-section superelevation, which is basically just the banking of the road on curves. So think about it. The next time you safely take a curved off-ramp at speed and your car doesn't go flying outward, you have those exact superelevation calculations to thank for keeping you grounded.
Section 3. Pavement and rehabilitation, the infrastructure doctor.
All right, out in the field, this is where the rubber literally meets the road. Now, what's really interesting is the stark contrast between the two main physical materials engineers use out there. On one hand, we have rigid pavement, which is concrete that uses reinforcing dowels and intricate joint seals to handle movement. On the other hand, there's flexible pavement, which is a layered asphalt structure. Each one has completely different engineering properties and lifespans when faced with the blazing sun and the constant pounding from heavy tires.
But how do they know how thick to make them? Well, engineers definitely don't just guess. They rely on intense mathematical models like the incredibly detailed AASHTO nomograph. It's a calculation tool used behind the scenes to predict the pavement's service life. They chart variables like the estimated total 18-kip equivalent single-axle load applications, which is just a highly specific way of measuring how much heavy truck traffic the road is going to see. They combine that with the resilience of the roadbed soil and scientifically determine the required structural number for the pavement.
But hey, even with perfect math, roads still deteriorate over time. If we ground that complex math with a medical analogy, we can imagine a patient in distress, a cracked, failing roadway. To figure out the root cause, field crews take a physical pavement core. Just like a medical biopsy, they drill down with the heavy rumble of a core drill, extract a solid cylinder of the pavement, and analyze it to see if they're dealing with joint deterioration, moisture stripping, or a deeper structural failure.
So what exactly are they diagnosing? Well, our highway patients suffer from a pretty specific list of daily ailments. Engineers are out there looking for block cracking, rutting where the wheels travel, those dreaded potholes we all absolutely hate, raveling of the surface, bleeding asphalt, and punch-outs in continuously reinforced concrete. These are simply the inevitable structural deteriorations caused by heavy traffic and harsh weather over the years. Of course, treating all these ailments takes a whole lot of capital. That's where a life cycle cost analysis comes into play, comparing rigid concrete versus flexible asphalt alternatives at various discount rates. It really goes to show that engineers aren't just looking at the initial price tag of construction. They're meticulously balancing the long-term maintenance, rehabilitation, and user costs over the highway's entire decades-long lifespan.
Section 4. Engineering Roadside Safety, the Shield.
Okay, so we've built the road and we've maintained its skin, but now it's time to focus on the human element. In engineering terms, roadside safety design involves treatments applied to the area beyond the traveled way. Think of this space as a critical, highly engineered buffer zone. It's designed entirely to forgive human error and minimize injuries when a vehicle inevitably runs off the road.
To create that forgiving environment, engineers use a whole toolkit of life-saving interventions. They design clear zones, applied to slopes, which gives a car room to safely recover. And when they just can't remove an obstacle, they install roadside barriers, median barriers, heavily tested bridge railings, and those impact-absorbing crash cushions. Remember that 1/3 fatality rate we talked about at the very beginning? Well, these specific safety interventions are the exact reasons those fatalities have plummeted so much since the 1960s.
We've really covered some ground today, haven't we? From strict environmental laws to mathematical curves, and from pavement biopsies to life-saving crash cushions. It is a massive, highly coordinated symphony of engineering. So, I'll leave you with this to ponder the next time you get behind the wheel. What unseen continuous engineering life cycle is happening right beneath your tires on your commute today? Thanks so much for joining me on this explainer, and keep your eyes on the road.